In the previous video, we were thinking about using a voltage divider to convert the change in resistance of a strain gauge to a voltage. And we looked at two problems. One was that the output of the voltage divider had a very small signal riding on a large fixed signal, and it was the small signal that we wanted to amplify. Another issue was the effect of source impedance on the output of the voltage divider. Now both these problems are sorted out by using a Wheatstone bridge. What's a Wheatstone bridge? A Wheatstone bridge is essentially a circuit as shown here, and it has got two voltage dividers in it. So think about this, R1 and R2 make a voltage divider, and similarly R3 and R4 make a voltage divider. And the power supply for both the voltage dividers is the same. And what we do is, as the output of the Wheatstone bridge, we take the difference of the voltages of these two voltage dividers. Okay, so the voltage at point A is given by R4 over R3 plus R4 into V, and the voltage at point B is given by R2 over R1 plus R2 over V, and you take the difference between the two and you have the output of the bridge. Now for a balanced bridge, that is when the ratios R1 is to R2 is the same as R3 is to R4, the output voltage is going to be 0. So we can use this Wheatstone bridge to convert the change in resistance because of the strain gauge into voltage. And to do that, what we do is we take a strain gauge and we put it instead of the resistance R4. So R4 is a strain gauge. And if we substitute the resistance of a strain gauge, which is R0 multiplied by 1 plus X, into the output equation for the output of the Wheatstone bridge, you can do some analysis. And if you assume that the ratio of the resistors is K, what you end up is with this voltage. And if we assume the same assumption as previously, that X is much smaller than 1 plus K, then the fixed voltage here in this term cancels out, and what we get is V0 is X over K plus 1 into V, which means that the output voltage is dependent on the changing on the change in resistance without a fixed voltage being added to it, which is one of the problems of the voltage dividers sorted out. How are we going to use Wheatstone bridges in reality? So here's a strain gauge, and what we do is we just run wires from the strain gauge to the Wheatstone bridge and connect that into the Wheatstone bridge and measure the output, and that would give us the change in resistance. What would happen in many cases is that a strain gauge will not only change its resistance depending on the strain, which is measured by this X, but it will also have some kind of a temperature dependence. Okay, so the strain gauge changes its resistance. There's another additional term in that, and that is 1 plus Y. So the resistance of the strain gauge is R0 1 plus X multiplied by 1 plus Y, where Y is the fractional change in resistance due to the temperature. Now, is there a way in which we can use the Wheatstone bridge to cancel out this effect of temperature? Yes, there is. And what we can do is we can put strain gauges instead of two of the resistors. So one of these resistors is measuring the strain, and it also has the inadvertent change in resistance because of the temperature. Another of these strain gauges, what we do is we make sure that it does not measure any of the strain, but because it is in the same environment, it measures the change due to the temperature. Okay, and if you look at the output of this Wheatstone bridge, the dependence on the temperature is reduced quite a bit. I'll leave the maths to you. Basically, you have to write the voltages of both the voltage dividers and subtract them to get the output of the Wheatstone bridge. Instead of connecting another strain gauge in a place where there is no strain, as we saw in the previous picture, we can connect a strain gauge on the opposite surface to the first strain gauge. And what this surface experiences a strain in an opposite direction to the top surface. When the top surface is expanding, the bottom surface is actually contracting. So the resistance changes have opposite signs. And when we put these strain gauges in a Wheatstone bridge and do the maths, we see that the output is linear. So in the previous cases, we had to make an assumption, and because of that assumption, we got a linear output. But in this case, the output is linear completely without any assumptions. Instead of using 2 strain gauges, we can use 4 strain gauges, so that all the resistances in the Wheatstone bridge are actually strain gauges. And what that gives you is it increases the sensitivity of your measurement. It would be an interesting exercise for you to see what happens if each of these resistances has a temperature dependence, 1 plus y as well. Does the temperature dependence cancel or not?